Welcome back to the third lecture in the series on basic data science modules. We're carrying on our discussion of NumPy by examining why NumPy is useful, why NumPy arrays in particular are useful compared to built-in Python data structures. So compared to a list, so far it seems like arrays are much less flexible than lists. Arrays must be rectangular, and they have to have homogeneous data type. So that's much more restrictive than a Python list, which might leave us wondering, why would we want to use them? These restrictions are related to how an array is stored in memory. Just like with a set, when we introduced the set, I discussed that it was unordered and said, why would we want to give up the ordering of the set compared to a list? And it turned out that by giving up the ordering, we could improve how the set was stored in memory for search, for instance, for certain operations that we might want to do. We have a similar case with the NumPy array. NumPy arrays are stored in contiguous blocks of memory. And every element of the array uses up a uniform amount of memory. Compared to a Python list, it's not possible to know in advance how much memory we will need to allocate for the list, or how much memory we need to advance through to go from one element to the next. Because a Python list can have heterogeneous objects inside of it that all take up different amounts of memory. With a NumPy array, since every element has the same data type, it all takes up the same uniform blocks of memory. This allows us to iterate very quickly over the array. In fact, NumPy arrays are implemented not in Python, but in C. So Python is capable of interpreting C code, and NumPy uses that feature to its advantage to define arrays in C, which allows for very fast iteration over the array. Another advantage of having a uniform data type is that we know that all the elements of the array will have a uniform interpretation of mathematical operations. For example, if I have a Python list and I want to do a sum on the list, I can do it. And what happens is 6 gets added to 3.4 to give me 9.4. And then I add true, which is coerced into a 1 to give me 10.4. But each time Python is stepping through this list to add up the numbers, it has to check what the interpretation of addition is for each of these numbers. 6 plus 3.4. Do these numbers agree on what plus means? And what about true? Will the result of this addition agree with what true thinks plus is? So at each step in the sum, Python has to check whether or not this plus can be performed and how it should be performed. With a NumPy array, we know in advance every element defines addition in the same way. And this lets us do addition much more quickly because we don't need to be doing this interpretive step or this lookup with every step of the sum. So let's see in action how this efficiency works out. So I have a list and an array. They both contain a bunch of random numbers. So I generated a bunch of random numbers here using the random submodule of NumPy. We'll talk about that in a moment. So I generated 100,000 random numbers, a random number for each number that I don't care about in the range from 0 to 100,000. And then I took that list and I turned it into an array, so I have the list form and the array form. If I want to add up all these random numbers in the list, on average it takes me half of a millisecond, 500 microseconds on average. Using the array, it takes me only 10% of the time it took for the list. It's 10 times faster. 50 microseconds. So that's a pretty significant speed up, 10 times faster. And that's because all of the NumPy knows, since this array has data type float, it knows all of these numbers are going to agree on what addition means. And additionally, using the C backend of NumPy, it can iterate very quickly through the array, adding up these numbers. So those are some significant computational gains that we can access by using NumPy. Now, another thing that's not totally clear here, but if we go back to where we were, is that NumPy also, the array, NumPy array, is going to give us a much better syntax for performing computation on collections of numbers. Down here, where we just have a list, the syntax looks almost the exact same. Here we have a sum of our list of numbers. Here we're using the NumPy sum function on an array of numbers. So this looks the exact same. Almost. But as soon as our array has more structure than a single list, it becomes much more syntactically clear when we're performing calculations compared to working with, for instance, a list of lists. So to remind you, in the previous video, we defined a list of lists with the numbers 1 through 9 as a 3 by 3 array. If we wanted to calculate the total of all these numbers in the list of lists, we would have to iterate over our list of lists, and for each inner list, we would perform a sum. And then, once we had performed the sum of all the inner lists, we could sum up those numbers now contained in the outer list. So we would do a sum of a list where we summed the inner list for each inner list in our list of lists. This is awful. this is really difficult to understand and not very clear. In contrast, if we want to sum up all the numbers in an array, we can just do our array.sum. Now, let's say maybe we don't want to add up all the numbers. Maybe we just want to add up the rows. Well, then it's not so bad for the list of lists, right? I could just do sum inner list for inner list in list of lists. Not as bad. So here's the sum of the rows, 6, 15, 24. But I still had to do an iteration at least. I had to do a list comprehension. Again, with the array, it's quite a bit easier. Whoops. There we go. I can perform a sum along a particular axis of the array. So if I want to add up the rows, I do a sum distributed across axis 1, meaning across this way. So I add up all the rows. What if I wanted to add up the columns? Here with the list of lists, we're really into trouble. I would have to do something like sum row index for index in range length of lists say 0 for row in list of lists. I think this should work. No. Int is not iterable. For index in range, right. So like this perhaps. There we go. So now I've got a sum of all the columns. I iterated over the indices of the columns, 0, 1, 2. And for each index, I iterate over the rows, accessing the row at that column index, and I perform a sum. This is not only very difficult to read and understand, but it was so difficult to understand that I could not write it correctly the first time. The first time I tried to do it, I did it incorrectly. It's so much easier with NumPy. I'll just perform a sum along the columns, or across the rows, say, down the rows. Yeah, so NumPy gives us a much nicer syntax for performing mathematical computations because NumPy, numerical Python, is designed with doing these kinds of computations in mind. A list, or any of the Python built-in data structures, are very generic, general data structures intended for use in a wide variety of ways, whereas NumPy is specifically meant for working with numbers, numerical data. And in particular, kind of something sort of like a table of numbers. And we'll extend that idea even further when we get to pandas, which makes use of this array structure to really bring the idea of tables to Python. So another reason to care about NumPy, beyond the fact that it enables very efficient mathematical computation and provides a very nice syntax for doing so, is that it's the basis for many other Python data science packages. So that concludes our discussion of why NumPy. Why should we care about NumPy? What does NumPy have to offer us that makes it so compelling? In the next video, we'll continue to explore doing mathematical computations with NumPy, getting into data transformations and aggregations.